Event horizons as interfaces, not walls. Event horizons are often described in language that suggests finality, a boundary where things end, a point of no return, a wall beyond which nothing exists in any meaningful sense. This paper replaces that imagery with a more precise and less misleading one. An event horizon is not a terminal wall in space-time. It is a geometric interface, an orientation change in how space-time paths are arranged, where the relationship between inside and outside is redefined rather than severed. What changes at the horizon is not existence, but accessibility. In general relativity, an event horizon is defined by causal structure, not by material composition. It marks the surface beyond which future-directed paths no longer intersect distant observers. This definition says nothing about destruction, erasure, or annihilation. It only states that outward communication, as defined by the external geometry, ceases. Treating the horizon as a wall smuggles in assumptions that are not present in the mathematics. There is no physical barrier, no shell, no surface that matter collides with. The horizon is a feature of how space-time is oriented. Describing the horizon as an interface captures this more accurately. An interface separates regimes without eliminating continuity. On one side, space-time paths can loop outward and reconnect with the broader universe. On the other, all future-directed paths point inward. The horizon is where that orientation flips. Crossing it does not involve a sudden event in local physics. Locally, nothing special happens. What changes is how paths relate to the rest of spacetime. The interface marks a translation in connectivity, not a termination of motion. This distinction matters when interpreting statements like "nothing escapes." That phrase is correct in a specific external sense. No future-directed signal from beyond the horizon can reach distant observers. But it is incorrect if interpreted as nothing continues. Motion continues, processes continue, trajectories extend. They are simply redirected into a region that is no longer externally connected. The horizon enforces one-way translation, not destruction. Confusing these leads to unnecessary paradoxes. Viewing the horizon as a membrane rather than an edge helps maintain continuity without overstepping known physics. A membrane separates domains while still being part of the same structure. It allows passage in one direction and not the other, depending on orientation. The event horizon behaves similarly. It is not a place where space-time ends, but where space-time's causal alignment changes. The outside and inside are still part of the same geometric manifold, governed by the same underlying rules. This framing does not claim that interior regions are observable, understandable, or accessible. It does not resolve debates about firewalls, information loss, or quantum effects at the horizon. Those questions are intentionally deferred. The claim here is narrower and safer. External physics already treats horizons as geometric features of causal structure, not as material walls. Reframing them as interfaces aligns language with mathematics without adding speculative content. Information provides a useful lens as long as it is handled carefully. Translation does not imply preservation in a usable form, nor does it imply recoverability. It simply means that information is not destroyed at the interface by definition. The geometry redirects how information-bearing trajectories evolve. Saying nothing escapes describes an external observational limit, not a statement about what continues internally. The interface separates observational domains, not existence itself. This paper exists to keep continuity on the table without violating known constraints. Treating horizons as walls forces premature conclusions and artificial paradoxes. Treating them as interfaces preserves what general relativity already allows: a smooth spacetime with regions of differing causal orientation. Later work may address what that implies for interiors, quantum behavior, or ultimate consistency. For now, the essential point is simple. An event horizon is not the end of spacetime. It is where spacetime changes how it points. Established general relativity already defines event horizons in a way that aligns naturally with the idea of an interface rather than a physical boundary. An event horizon is not identified by any local material feature, stress, or surface property. It is defined purely by causal structure, the set of points beyond which future-directed null and time-like geodesics cannot reach distant observers. This definition, formalized within the framework introduced by Albert Einstein, makes the horizon a global geometric feature, not a local abstraction. Nothing in the theory treats the horizon as a wall, where motion halts or physics breaks. One of the strongest supports for the interface interpretation is the equivalence principle. According to general relativity, freely falling observers crossing an event horizon experience no locally detectable discontinuity in spacetime. There is no sudden force, shock, or barrier encountered at the horizon itself. Local physics remains continuous. This would be impossible if the horizon were a literal wall or terminal boundary. The absence of any invariant local marker confirms that the horizon represents a change in global connectivity, not a physical endpoint. Mathematically, horizons arise from how light cones tip and reorient near strong curvature. Outside the horizon, future light cones include directions that point outward toward infinity. At the horizon, those outward directions asymptotically disappear. Inside, all future directed paths point inward. This is an orientation change in spacetime geometry, not a cessation of paths. Trajectories continue smoothly across the horizon. They simply evolve into a region that is no longer externally connected. This behavior is exactly what an interface does. It separates domains of causal access without destroying continuity. Classical black hole solutions reinforce this picture. In solutions such as the Schwarzschild geometry, the horizon is not associated with any divergence in curvature or local physical quantity. The true geometric singular behavior, if any, lies elsewhere. The horizon itself is a coordinate-independent feature of causal structure, not a material surface. Its properties depend on the global arrangement of spacetime, which is why different observers can disagree on when or whether a horizon is formed. Such observer dependence is incompatible with the notion of a rigid wall, but fully consistent with an interface defined by connectivity. The statement "nothing escapes" is also formally limited in scope. In relativistic terms, it means that no future directed signal originating inside the horizon reaches future null infinity. It does not state that trajectories end, that processes cease, or that information-bearing paths are annihilated. Worldlings continue beyond the horizon. Fields evolve. The restriction applies only to outward communication relative to external observers. This asymmetry is a hallmark of causal interfaces, not terminal boundaries. Even discussions of horizon-related thermodynamics implicitly support this interpretation. Horizons are treated as surfaces, encoding relational properties between regions, not as hard edges in spacetime. Quantities like horizon area are associated with external observables, not with internal destruction events. While deeper questions about quantum behavior are intentionally excluded here, the classical framework already treats the horizon as a bookkeeping surface separating domains of description. Crucially, nothing in this support requires claims about observable interiors, firewalls, or resolutions of the information paradox. The argument rests entirely on external geometry and causal structure, both of which are well tested. General relativity consistently models event horizons as smooth, non-material features where spacetime orientation changes globally while remaining locally continuous. Taken together, the equivalence principle, causal definitions, light cone behavior, classical solutions, and observer dependence all point to the same conclusion. An event horizon is not a wall where things stop. It is a geometric interface where access changes, motion continues, information-bearing trajectories persist, and spacetime remains intact. What ends at the horizon is not existence, but outward reach. From funnel to rupture, black holes as dimensional apertures.